Chapter 9, Part 1, Principles of Joints and Sealants. Building joints result from our need to work with materials that can be easily and efficiently fabricated, transported, and assembled on site. The joints also allow field adjustments in assemblies during construction. Additionally, visible connections resulting from the joints provide an opportunity to develop ideas of scale, pattern, color, texture, and so on building planes and surfaces. The most important issue in the design of building joints is that the dimensions of the building components are constantly changing, not only with respect to their original dimensions, but also relative to each other. For example, window glass expands and contracts in response to external temperature changes. The changes in glass dimensions are usually different from the corresponding changes in the frames that hold the glass, yet we still need to be able to make a secure connection between the window glass and the frame. Here are three examples of static joints. In example A, joints are a common feature in buildings, particularly on facades. Some of these joints are aesthetic joints to provide surface relief, rhythm, patterns, and so on, while others are provided for performance reasons related to the building design and/or for construction. B, the fasteners used in the joint in the copper cladding of the Burton Barr Central Library in Phoenix, Arizona, contribute to the rhythm and pattern in the cladding. And C, the textured surface and the bold horizontal lines in the exterior concrete walls of the same library building relieve the monotony of large concrete surfaces. A static joint is a non-moving joint or connection between components. In the case of the window glass in the frame, a static joint would most likely result in broken glass, a broken frame, or possibly both. Dynamic joints or movement joints are connections that allow both materials to move independently and at the same time hold the window glass securely to the frame. Let's take a look at the different types of movement joints. Based on the purpose they serve, movement joints are classified as building joints, joints between different parts of the building as a whole, and component joints, joints between individual components of an assembly. A building joint divides the entire building into two or more separate buildings. Based on the purpose for which it is provided, it is classified as either a building separation joint or a seismic joint. A joint between two adjacent building components can be an expansion joint, a contraction joint, also commonly called a control joint, or an isolation joint. A building separation joint prevents the stresses created in one part of the building from affecting the integrity of the other part. Building separation joints are needed in large buildings, and as a rough guide, they are provided at 250-foot intervals. Building separation joints are provided at the following discontinuities: where low building mass meets a tall mass, where the building changes direction, such as an L-shape or a T-shape building, where the building structural material changes, such as where a steel frame building meets a concrete frame. Building separation joints typically run through the entire building from the ground floor or the basement if provided, up through the roof. Separate columns are often used at separation joints. However, a combined footing may be used for both adjacent columns. This is an example of a building separation joint with two columns in a reinforced concrete building. Because the building is under construction, daylight is showing through the joint, between the columns. In a completed building, the joint is sealed and covered with a joint cover, as is the case here for the separation joint in the floor. This is an example of a building separation joint with 2 columns and 2 beams in a steel frame building. This is an example of a building separation joint that uses a single column in a reinforced concrete building. Observe the provision of a beam on each side of the separation joint. A seismic joint is similar to, but also different from, a building separation joint. Building separation joints accommodate moderate building movements caused by temperature and moisture changes, creep, and foundation settlements. Building separation joints are designed to accommodate mainly horizontal movements, that is, in the direction perpendicular to the joint. Seismic joints. The purpose of seismic joints is to ensure that one section of the building does not collide with the adjacent section during an earthquake. A seismic joint must accommodate simultaneous movements in horizontal as well as vertical directions, that is, in all 3 principal directions. A seismic joint is generally much wider than a building separation joint. So, the primary difference between seismic and building separation joints is that building separation joints primarily act laterally, where seismic joints have to be designed to act in multi-directions in all 3 planes. Seismic joints are also bigger than building separation joints. This is a typical detail of a building separation joint cover at the floor level. Similar covers are provided in interior and exterior walls and roofs. Joint cover manufacturers' details and specifications should be strictly followed for structural, fire rating, and other performance reasons. Let's take a look at movement joints in building components. Movement in a building component can be caused by several phenomena. Factors that must be considered in sizing and detailing movement joints in building components include thermal movement, moisture movement, elastic deformation and creep, construction tolerances, and other considerations. In common construction materials, steel, concrete masonry, brick masonry, and wood, several different movement types must be considered in designing structures using these materials. For example, with steel, thermal and elastic deformation must be considered in the design of the movement joint. In concrete masonry, thermal, elastic deformation, creep, and reversible moisture must be considered in the design of construction joints. Where X is indicated, the presence of a particular movement must be considered in that material. When a material is restrained and not allowed to move, even the smallest expansion can cause large lateral deformation in the member. Note that when placing 2 25-cent coins, one at each end of the acrylic member, the amount of deformation is equal to approximately 2 inches. It is much larger than the longitudinal shortening by approximately 1/8 of an inch. So let's take a look at expansion and contraction control with thermal movement. To determine the thermal expansion or contraction of a component, we must assume that its length is L and that the temperature change it experiences is delta T times degrees Fahrenheit or degrees Celsius. If the component is not restrained, its length will increase or decrease, so that the new length will be the length plus delta T or length minus delta T, where delta T is the change in length. The value of delta T is given by the following equation. Delta T equals alpha length times delta T. The figure 8 looking Greek symbol is actually the lowercase delta symbol. So it's the same as the triangle. The coefficient of thermal expansion for several commonly used construction materials can be found here. Depending upon the location and the time of year that the material is installed, the material will always experience a swing in temperature change. For example, if it's installed in the winter, it could be that the material itself will change temperature up to 90 degrees Fahrenheit. And that's going to be the worst case scenario. If you take a look at the diagram in your text, 90 degrees Fahrenheit is the worst case scenario in terms of temperature differential. In one of the examples in our text, a residential neighborhood is to be provided with a clay brick masonry noise barrier along a busy road. It's been decided to use 100-foot long segments of the wall with intervening joints. Determine the required width of each joint considering only the wall's thermal movement. So if our length is 100 foot, we have to change that to inches. If we take 100 times 12, we end up with 1200 inches. Our change in temperature, our worst case scenario, based on the diagram shown in the previous slide, is 90 degrees Fahrenheit. The coefficient of thermal expansion for the clay wall, is that correct? Clay, I think it is, clay brick wall is going to be 4 times 10 to the negative 6 power. So we multiply the coefficient of expansion with the length and the change in temperature, and we get a total width of 0.432 inches. That's the amount of expansion we can expect to see in the 100-foot long wall. That joint we should round it up to a half of an inch. So the joint width is going to be a half inch. So in the previous example, each segment of the 100-foot clay wall would have to have a joint that's at least 0.432 inches wide. And again, we would round that up to a half inch. In example 2 in your text, a brick veneer wall is provided with continuous vertical expansion joints at 25 foot on center. Determine the required minimum width of each joint, considering the thermal expansion of the wall. So if our length of our wall is 25 feet, we have to multiply that by 12 to show the length of the wall in inches. And our annual temperature change is going to be 90 degrees Fahrenheit. That's our worst case. And then from equation 1, the joint width is clay coefficient of expansion is going to be 4 times 10 to the negative 6 power times 300 times 90. And so our length of the joint, or the width of the joint, should be 0.108 inches. So a quarter of an inch is going to be 0.25 inches. So that expansion is going to be less than an eighth of an inch. We'd probably just go ahead and make the width of that joint 3/8 of an inch. This is the end of Chapter 9, Part 1. Go ahead and complete Chapter 9, Part 1 quiz now.